basic idea of the scattering. So you are having a particle that is completely free, okay, and it hits a target, and that target will represent by a potential, and that potential decays up to zero, okay, goes to zero in the asymptotic limit, or it is localized in certain region, and beyond that region there is no potential. And once this incident particle hits the target, and you are having then a scattered particle, okay. In quantum mechanics, you represent the particles by either by waves as well as by particles. Clear? Okay, so say if I consider now the spherically symmetric potential, okay. So let's consider a spherically symmetric potential. That means our target is represented by these centrosymmetric potentials. For example, let's say you are having the Coulomb potential generated by the nucleus. Clear? So the potential outside the nucleus is spherically symmetric. Think of the alpha particle. Okay, so that's a charged particle that is scattering of that nucleus. What is happening? So you are having a particle going into the domain of that very potential, ultimately leaves. Clear? So that's an ideal situation kind of thing, or a basic example of this scattering of the this spherically symmetric potentials. Okay, so now the wave what you receive after the scattering, that is spherical wave. Okay, so we have seen in general, you are having this kind of, suppose if you are having a wave that you observe at the end of the scattering, you are having like this thing, a spherical outgoing wave. Clear? Okay, so let me write only F for the time. F is the amplitude. So when you are having our scattered wave as an outgoing wave, and the incident wave is a plane wave, okay, a particle which you, it's we consider only a single wave here, but it's not true. It's actually a wave packet. Clear? So you represent this incident particle by a wave packet. Clear? And the outgoing wave is actually a spherical wave. Now what I want to do, I want to analyze. Okay, so if I am having a spherical wave, you can think there is actually a phase shift, the shifts in phase arising once the particle scatters. Let's say if you are having a wave that hits some scatter somewhere, some potential, okay, and once it leaves, so it's a consequence of this very scattering, there may arise a phase change. Clear? And you need to compare these kind of phases. A change in phase related to this incident wave. But if I am saying this as a plane wave, a particle represented by a plane wave, but outgoing wave is a spherical wave. Clear? Okay, I want to bring this incident wave in terms of the spherical waves. I want to write this incident wave in terms of the spherical waves. Outgoing waves are spherical waves, then you can compare the two because the nature of the wave is the same. Clear? And this kind of phenomenon, okay, so this kind of representation we call as the partial wave analysis of the scattering. Okay, so you represent your waves in terms of the partial, just it is, okay, so think this way, classically. Suppose if you are having, let's say a spherical scatter, a pinhole, that's a spherical in nature. So once you scatter the light through that, what are the nature of the wavefronts? So those are the spherical wavefronts, okay? But you can, that means you can represent, let's say, the incident wave, you can always express in terms of the spherical waves. Okay, if you need to check how much phase change is there, so the basis must be same. You are having a spherical basis, okay? So the wavefronts, you observe actually the change in the, okay, so nature of the wavefronts, okay? So the basis in which you compare the change in phases, it must be same. Clear? It must be identical. Now let's say if you are having simply a wedge, or let's say instead of a pinhole, you are having a line as a silt. So the wavefronts will be actually cylindrical in nature. In that case, you do your analysis, you express your waves in terms of the cylindrical waves or the cylindrical wavefronts. Clear? Got it? So this is the crux of what we call this partial wave analysis or the wave analysis simply. Yeah? Okay, and it is actually this kind of analysis very useful when you do the low energy scattering. If you are doing high energy scattering, then it may not be suitable, but low energy scattering, it's very suitable. Okay, so I will give you an example of low energy scattering. You know the I mean, if you are condensing, let's say, atoms to a Bose-Einstein condensate, you are cooling down the atoms. Okay, so once you cool down the atoms, ultimately it is actually a scattering process. So you hit atoms by the laser light. Okay, there is an interaction between light and the atoms. Okay, so you can observe that kind of scattering process, or you can think what are the interactions between the atoms itself at that very energy levels. Okay, so calculating the cross sections, it is very useful to do the partial wave analysis. Okay, so suitable way is to do the partial wave, because you will consider the phase shift is arising. Okay, once the system cools down. Okay, so let's say technically complicated example, but this is how we are analyzing. Let's say you are having electrons. Okay, so let me give another example instead of this. Suppose you are having a Cooper pair formation. Clear? So it's actually the scattering of two electrons which exist in the opposite spin states. Okay, but they are diametrically opposite to each other at the Fermi surface. Clear? So there is a scattering between these two particles. As a result of that scattering, they get bound. Okay, so there is this weakly bound state is being formed. Okay, so if you analyze that kind of scattering, so the best way to do is that to look at this phase change. Okay, do the partial wave analysis. Clear? Okay, so we'll see actually it emerges into it goes into the angular momentum state s equal to 0, this Cooper pair. Okay, so the most dominant process turns out to be s equal to 0 state. Okay, okay, so we'll see that in terms of this analysis. Okay, so let's formulate our problem first. Okay, so this is the overview of the problem. Now, what actually we are doing? Okay, so we are having these three regions. So let's say I'll first, do what you know. Okay, so I'll review first things of the spherical harmonics. Okay, so you are having an incident wave, okay, or the incident region. Then you are having actually the scatter. So these are the three regions given by some potential. Okay, so what is the condition of the potential here? So it is spherically symmetrical. And then you are having actually scattered. Okay, so what is the Schrödinger equation here? So you don't have the potential. So since we are in the three dimensions, clear? It's a three-dimensional problem we are doing. So it is simply like this. Psi that's equal to 0. So our K is how much? Twice ME by. Okay, so you are having a free particle solution here. That means if I am considering now free particle in three dimensions. Okay. So here, what is the Schrödinger equation? So let's try it. It is something E square minus E. Okay, so let me put it this way: twice M by H cross square E minus V of R. Because potential is non-zero here, so this is the region. And here again, what you are having, the same thing what you are having above. Okay, so we'll try to solve the Schrödinger equation in these two regions. Okay, let's begin with this thing. So I should. This is the scattered region, means the asymptotic limit R tends to infinity, where there is no potential. So, what's our nebula in this in spherical polar coordinates? Anybody? 1 by r square. Okay. Partial by partial r square. Partial plus. Then
1 by r sine
x minus L square divided by h cross square r square, where L is the angular momentum. So that means we are considering when I am doing the partial wave analysis, it means we are resolving our plane wave in terms of the angular momentum states. Okay, so remember this very point. Okay, so we'll be doing actually the scattering in the let's say, although there is this radial dependence, but ultimately we are actually looking the partial wave analysis itself means, so you have to look at the eigenstates of this L. Okay, so there is actually one mathematical reason why we do this partial wave analysis. For a free particle, you are having this L square commutes with the free particle Hamiltonian, P square by 2m. Clear? So that means angular momentum is conserved. And if you see, there is this LZ, this also commutes with what? So that means the good basis is what? Okay? L and LZ. Clear? Obviously, and the radial coordinate. And there is one more term, this S square also commutes with this. So it means this S is actually, the spin is diagonal. Or in other words, the Hamiltonian is diagonal in this spin basis. And that's why we are not considering here the spin states. We consider simply the free particle, okay, suppressing the spin degree of freedom. That means I am considering a spinless particle. Got it? Spinless does not mean you are not considering the spin. So it means I am suppressing actually here the spin degree of freedom. Okay? It's a general particle. So I have not considered the nature of the particle, whether it's a fermion or the boson. Okay, so that will take later. Okay, so now let's look at the solution of this very problem. So let's take this very equation. So let's solve this very equation. What are the solutions? Anybody? So my solution is, okay, I can always write this psi as the radial coordinate, okay, and the spherical harmonics, YL. Okay, so let's put in argument the R. So theta phi. Okay. So I know this spherical harmonic satisfies the angular momentum part of the equation, and this RL satisfies the radial. Okay, so I will write this RLR satisfies the radial the equation, the radial part of the equation. So what is that? So it's 1 by R square d by dr. Okay, R square d like this thing. Then plus, so you are in k square minus L into L plus 1 divided by R square. This we sometimes call it as the centrifugal term because it arises from the angular momentum. Okay, so this is our radial equation. And YLM, so these you know. Okay, so let me repeat it here. So it is something m plus magnitude of m by 2 root of 2L plus 1 divided by 4 pi. Okay, L minus m factorial divided by L plus m factorial. Okay, what this is? PLM. And while PLM are associated Legendre polynomials. Okay, so let me write that. So PLM x is equal to 1 minus x square raised to magnitude of m by 2 d by 3x magnitude of m PL of x. And this PL of x is what? Legendre polynomial. And this is associated Legendre polynomial. Okay. Clear? So now we can simplify this radial part of the equation. Okay, so we can simplify. So let me call, so let's simplify it. So like this thing, we can substitute this RL of R as some ULR by R. Clear? So let's substitute this RL as what? U by R. Clear? And substitute there in this equation. Okay, so in this equation what you get, so this you have already done, I am simply revising it. d2ul by dr2 plus k square minus l into l plus 1 by r square. So now you see it is, let's call this as 1. So it looks like as a one-dimensional equation which depends on what? Yeah, the solutions will depend on that. Okay? Can anybody tell me what is the solution? Okay, now first tell me what is the boundary condition? We have not specified the boundary conditions of the problem. What is the proper boundary condition of this problem? I am having a spherically symmetric potential. Okay? So what is a boundary condition? Boundary condition means what is the condition you impose on the wave function. What is that? So what kind of condition is that for this kind of potential? So at the center of the potential, okay, so the wave function must vanish. Clear? So because at the center, let's say if I am having a spherically symmetric potential, let's think of the Coulomb potential 1 by r. Clear? What is happening to the potential at the center, at the origin? That's r tends to 0. It blows up. Clear? So when the potential becomes infinite, so wave function must vanish there. Clear? So that means particle does not exist there. So that's why we require that kind of boundary condition. Okay? Okay. So it means, okay, so if I require wave function to vanish at r equal to 0, so this is the part which depends on r. Clear? It means RL at r equal to 0 must vanish. So in other words, since we are transforming the equation in U, so our boundary condition means UL at r tends to 0 has to be equal to 0. Clear? So this is our boundary condition. This is a very important condition. Clear? Okay. So now let's simplify it a little more. Okay, I want to remove this k here. Okay, so you can put, let's say, take k out, what it will attack here? K square r square and k will come here. Clear? So let me use a variable. So let's put y is equal to kr. Okay, so how it looks like? So my equation will be simply du like this thing, y2 plus 1 minus L into L plus 1 by y square into UL, that's equal to 0. Now it's a nice formula. So if anybody can recognize this equation, it's a standard differential equation. It's a Bessel equation. Okay, good. So what are the solutions? Now tell me. So now the solutions of this very equation are, so let me write U, L, Y. Can anybody tell me what is the solution? So the solution is actually the spherical Bessel function. Clear? Okay. So that's actually equal to U, L, K of R. So that's equal to, so you need to multiply. It's actually, it's really not a Bessel equation. It's a modified one. We call it as a Riccati-Bessel equation. Clear? So because you are having y square here, it's a Riccati-Bessel equation. So the solution is actually the Riccati-Bessel functions. Okay, so those are actually the spherical Bessel functions multiplied by the variable appearing here. Clear? This y, like this. So it's some kr. Kr is actually y. Clear? So then let me write it as some constant a1 j kr. Okay, and dependence on this L plus, let's say, a2. So what is the another Bessel function called? Spherical. So there is a name for that. So this is spherical Bessel function. The another one which just differs by a phase. So that's Hankel function. You know it? So N L A R. Okay. So this is the most general solution of this very equation. Clear? Okay. So now let me write the form of this Bessel functions. spherical Bessel function. These are spherical. We call those as actually we call this as a spherical Bessel function of first kind, and this is second kind. That is known as Hankel function. Okay. So this JL, JL of x, it is defined like this thing: minus x raised power L. Have you seen this equation in our mathematical physics course? Yes. Sin x by x, and this NL of x, that's simply equal to minus x raised power L d by 1 by x, okay, d by dx raised power L cos of x by x. Okay, so now let's take n0 term. So what is that equal to? So it is minus cos of x by x, and what is n1 term? Minus cos of x by x square, okay, minus sine of x by x. So it means when you take L equal to 0, look here, L equal to 0, L, this is 1, it is simply cos x by x. Take n equal to 1, it is simply differentiation of this object, it will give you 2 terms. Clear? Okay, similarly, let's take this J0. Let's take J0 of x. So what is that equal to? Sine x by x. What is J1 of x? So what will be that? So just differentiation. So it is simply sine x by x square minus cos x divided by x. Clear? So and so on. This is how you can figure them out. Okay? Clear? Okay, so now what we need to do? We need to check. Okay, so we have to apply now the boundary condition. So this is a linear combination of the two functions which will give rise to the solution, and we have to check for the physical solution. Okay, physical solution means which will obey the boundary condition. Now if I take, now let's look at when I take x tends to 0. Let's take x tends to 0, J0 of x. Let's take the first one. So this tends to 1. Clear? So this also converges. Clear? So when you take x tends to 0, what about this thing? It's 0. Yeah, it's 0 because you will be having a 1 by x here, 1 by x here. Clear? So that will be 0. So that means this J L of kr, when r tends to 0, this goes to 0. Clear? Now let's look at this NL kr. When x tends to 0, so this diverges. It's cos x by x. Clear? So that means this very object tends to infinity. Yeah? So we are having, okay, so now let's apply the boundary condition. Okay, so if I apply now the boundary condition, what is that? UL of kr is equal to 0 for r tends to 0. Clear? So it means my JL kr tends to 0 in this limit, and NL kr diverges. Okay? Got it? So that means this term does not go to 0. Then what you do? You put A2 equal to 0. So which implies therefore this A2 is equal to 0. So therefore our solution is UL kr. Okay, so that's equal to sum. Okay, so let me forget about this A1. I will introduce it later on. Let me write A1. Okay, JL. So this is the solution of the equation. Okay, but U is not our solution. What is the solution? R. Clear? And one more point. Now let's look at the behavior of this J0 for small, or this JL of x. Let's look at for the small x in general. Now look here. When you take x tends to 0, so this goes as 1. Clear? But there is no, do you think there appears some L dependence? Huh? So what is the behavior? So what is the behavior? It will depend upon, okay, so for L equal to 0, you don't need to check, clear? Because it tends to 1. But when you are having L, let's say L is positive, let's say L is greater than 0, then you need to check what is the behavior, clear? So let's look at that behavior. Huh? And can you tell me? So you are having near origin. So that means x tends to 0. So we are having this j L of x. So it goes like this thing. X raised power L for L positive and 1 divided by x raised power. Okay. Clear? So if I take L like this thing, why? Okay, so let me give the physical indication. What is the nature of the wave function when you move towards the center of the potential? So it should vanish, is it? Or it should, okay, so it should decay to 0. Clear? How it will do? Now let's say, okay, so usually you are having the wave function in the first orbit of the hydrogen atom. What is that? E raised power minus r kind of thing. Clear? So when you go r tends to 0. So what does that mean? You are figuring out what is the why if the particle is at the center of the potential. Clear? So does it go to 0? Huh? So then what should be the behavior? So it goes as a constant. Clear? So that means near the center so this is actually L equal to 0 term. I'm sorry. This is actually L equal to 0 term. So that means you are having a constant probability density around the center of this very potential. Although at the center of the potential it is 0. Clear? But near that very center, the probability cloud is constant. Clear? Now let's take the L equal to 1 case. That's important. L equal to 1 case is actually, I think, multiplied by R. Clear? Okay, so there is this kind of R. Okay, because you are having R parity. Huh? Got it?
Yes.
So, okay. So you are having R multiplied by this thing e raised power minus R. Okay, forget about this exponential. So that means when you move towards the center, this wave function behaves actually R. Clear? So at R equal to 0, what happens to the wave function? It vanishes. Okay? So you are having that node. Clear? Got it?
Yes.
Okay. So that means when you move towards the center of the potential, this R must go as what? R is for L. Okay? So if L is positive, because it will be then R is for, let's say, R square, R cube, whatsoever. Right? Got it? So this function vanishes at R equal to 0. So, but if this L is negative, there are actually two types of solutions admitted to this very problem. Okay? So one is like this thing. It is the behavior of the solution is like this thing. R is for L and R is for minus L minus 1 kind of thing. Okay, so this is the behavior of the solutions near the where? At the center. Clear? So when you take, let's say, what does that mean? Let's take y tends to 0. So it means your R tends to 0. So this is very large term. You can ignore this thing and then you solve this differential equation. Okay, so the behavior turns out to be like this thing or this thing. Clear? You got my point? Okay. So it is exactly the behavior of this very Bessel function. Okay, if I take this L positive, then it's actually R is for L kind of thing. Huh? When you take it as negative, it is like this thing. Okay? Got it? Okay. So any question here? So our point is this thing. Okay, and this will help us. So now let's write the total solution. Let's write the total solution of psi. This. Okay. So anybody, what is the total solution? So okay, so let's write this RL of KR. So let's write this RL of R. What is that? UL KR divided by, what was that? R. So what is UL? So just I have figured out. So it is the constant A1. Then you are having KR. JL KR divided by this R. So it means it is simply equal to K is a constant. Clear? A1 is a constant. So therefore I can write this RL. Let's forget about this constant. I will introduce it in a moment. So it is simply JL KR kind of thing. Clear? So we'll take this K in terms of the normalization constant. Okay? This A1. So therefore our wave function is psi. Okay? R theta phi. Okay, so what is that? So let me write this normalization constant now. RL, for RL I will write JL AR, and then you are having this YLM theta phi. Clear? So this is your wave function. Now the solution for the problem what we are having at hand. Clear? Okay, so what we need to figure out? This normalization constant. Okay, so let's write the normalization constant. So it means, so you are having so you are having like this thing, d3 of r psi star r theta phi, okay, psi of r theta phi, so that's equal to identity, just to the probability. Clear? Okay, so now let's write it. Can you pull up these curtains? So let's figure out this normalization constant. So substitute it there. So what you are having? So I'll be having r square dr 0 to infinity. Okay. So look here. So which is the term which depends on r? This term. So n will come as mod of n square. Got it? Then you are having this j l a r. Okay. Then so let's write. It is a square term because it's a real quantity here. Got it? Okay. Then what you are having? Integration over the solid angle. Okay. So it is YLM theta phi star YLM theta phi. Okay. So that's equal to 1. So what this object is equal to?
1.
It's equal to 1. Clear? So can you tell me what is the value of this very integral? So this is an integral, you have done it. So it's a very standard integral of the Bessel functions. Okay. So try it at home. So it's pi divided by r. Look at the r. So what it means? So it means n is equal to root of 2k by. Okay. Got it? Huh? So it is pi by 2k square, because you are having r square already here. Got it? So you can convert this integral, put kr equal to, let's say, z. Okay, so what you will get? So you put this kr equal to z. So then it will be in terms of z. So you ultimately get this kind of integral. So it is a very standard integral of the Bessel functions. Okay. So that means my wave function is root of 2k by 5. Okay. So this will be used. Okay. So now I am having what? The wave functions. Clear? So now I have figured out the solution. So what are these? So these are the eigenstates of our problem. Clear? So when I am having an eigenstates, what does it mean? It forms a basis. So now I have figured out actually a spherical basis. Okay, I have solved my Schrödinger equation in spherical polar coordinates. That means I have figured out the spherical waves. For every L, I am having a given wave. Clear? Okay, so now what is my incident wave? Yes. So incident wave is a free particle wave. It's e raised for I k z. Let's consider the wave along the z direction. So my particle is moving along z direction, described by this plane wave. Clear? So since we are in the spherical polar coordinates, that means I can express it in terms of the spherical basis. Okay, using this kind of basis. Okay. Now there is one important point when I am writing it in the spherical polar coordinates. Z is equal to r cosine of theta. So it depends only on this azimuthal angle theta. So it only depends on theta. So it does not depend on phi. So phi variable, if you look at the Schrödinger equation, so there are three variables, r, theta and phi. R gives you the radial coordinate and theta gives you the angular momentum. And the projection of the angular momentum is Lz. So that is given by the phi variable. Since this does not depend on that projection, that means it does not depend on Lz components. Got it? So what it means? It means when I consider the superposition of these waves, when I express this wave in terms of the superposition, I need to consider m equal to 0 states. Because incident wave does not have the Z component. It means the superposition what you write, so that should not contain M. So that should contain actually M equal to 0. Okay? So what it means? It means I can write this thing IKZ like this thing. Okay? Summation or, okay, L equal to 0 to infinity. So these are infinite number of L states. Then when I write the superposition, what should I write? Some constant, okay, which is to be figured out. Let's write AL. Then you write this psi L M is equal to 0. Because M is equal to 0. Got it? Samajh aa? Okay, when I put M equal to 0, what this is? M equal to 0, theta, phi. So what does that mean? That is simply actually PL cosine of theta. That's only the Legendre polynomials. Got it? So in other words, I can write it. Okay, so let me write it as L equal to 0 to infinity. So AL, so you are having root of this thing 2k by pi. Okay, JL KR, so it will be simply PR cosine. So it is actually the extension of a plane wave in terms of the spherical waves. Okay, everybody got it? Okay, so what I need to figure out? What is unknown to? Okay, so what is the interpretation of this air? What is the interpretation of air? What is the interpretation? So let's say if you write this psi is equal to summation of n a n phi. And what is the interpretation of this a?
Expansion coefficient.
What this coefficient is present? Probability? Yeah. These are probability amplitudes, huh? Such that the particle you can figure out in, you can find in the state phi n. Okay. So what is the now the interpretation of this here? So it's a mod of AL square actually give you probability of finding the particle in a L component of this wave. So this is actually a wave, spherical wave. Okay. So you can plot it. So what is P? Let's take L equal to 0. Okay. If I take L equal to 0, how it looks like? P0 of cos theta, that's 1. So what this J0 is? It's sine x by x. What is the graph? How it looks like? Huh? Yes. So when L is equal to 0, what is the graph? So it's sine x by x. So that means the state looks like that graph. How it is? Is it like this thing or it is like this thing? Huh? It's not a parabola. Huh? It's probably like this thing. So the state looks like this thing. That means one of the waves is like this thing. It is a superposition of large number of waves. So it is simply the Fourier series. Fourier series in terms of this kind of basis. Okay. By the way, okay. So let's move ahead. So now what I need to figure out this AL. How I can figure out this thing? This AL. Can anybody give me a hint? How I can figure out this AL? Can anybody give me a hint? What's a hint here?
Inner product by state not equal to L.
Not equal to L. That is 0.
Product of the real sign.
Equal to
Actual sign.
So how you figure out A and here?
Inner product by
Okay.
state equal to n.
Equal to
N.
zero. Yes. So you simply take inner product with the state phi n.
Fine.
Okay. So for all n. Okay. So when n matches n prime, then it's equal to 1. When n is not equal to n prime, it is equal to 0. So you'll pick up only one of coefficients here. Okay. So that which inner product you know here in this case? You know the orthonormality of this PL. They are orthonormal. So what is the condition of orthonormality here? Zero to 5 sine theta d theta sine of theta PL cos of theta PL prime cosine of theta. What is that equal to? 2 by PL plus 1 delta L prime. This is in the condition. So what does that mean? What I need to multiply this thing? What I need to multiply? Huh? I need to multiply this by PL prime cosine of theta, sine theta, and integrate over 0 to 5. Clear? So it means you are having 0 to 5 d theta sine of theta PL prime cosine of theta e raised to I k z. So let me write z as r cosine of theta. Okay. So what is that equal to? Summation L is equal to 0 to infinity AL. Then you are having this root of 2k by 5 JL to R. So you are having the 0 to 5 d theta sine of theta. Okay. PL prime cosine of theta PL cosine of theta. What this object is equal to? 2L by 2 by 2L plus 1. Let me write L prime delta LL prime. Now you sum over L. Okay. When you sum over L, L will be replaced by L prime. So it is simply equal to L is replaced by L prime. It is AL prime. Okay. Root of 2k by 5. So it will be JL prime KR. Okay, and there will be this factor 2 divided by 2L prime plus 1. So what we have got? AL. So you take this factor on this side. Okay, so now what I want to do, so you can take this factor and divide it by this. Okay, on this side you will get AL. Okay, now what I want to do, I want to look at this very function. So this is some well-known function. So anybody? Can anybody guess what this is? It's a well-known function. So what is the integral representation of the Bessel function? Okay, no issues. So we are having the integral representation of Bessel function. I hope you have done it somewhere, right? JL of x 1 divided by I raised for, it's iota, I raised for L, and twice I raised for L, like this, 0 to 5 d theta sine of theta e raised for I x cosine of theta dl cosine of theta. So that means this very object is what? Now tell me what this object is. It's a Bessel function, spherical. Okay, it is this spherical Bessel function in the integral form. So it means I can write this object as twice I raised for L JL KR. Clear? Because you are having x is here, KR. Clear? So what is our AL? So it will be L prime. Because I'm using L prime here. So it will be L prime. So it means I can simply write this AL as, because L prime is a free index. It appears throughout the equation. I can simply write it as AL. So it will be simply twice I raised for L, okay, into root of pi divided by 2k. Then you are having 2L divided by 2. 12 plus 1 like this. So 2 and 2 cancels. Okay? So what you are having? It's I raised by L root of 5 by 2k 2. This is our A. Clear? So now I can write this thing e raised power I k r k z. So this is the plane wave extension in terms of this spherical waves. So what is our AL? I raised power L. So here it was a factor of root of 2k by pi. That will cancel with that. Huh? Root. So it will be simply 2L plus 1 JL KR. So is there anything more? So sorry. So it is here a k square. Huh? It's a k square. It's a k square. Clear? So it's a k square. And this factor will cancel with this factor. Okay? So this is our plane wave extension in terms of. So we have not done yet the problem. Okay? So we have just expressed our plane wave in terms of the spherical polar coordinates. Okay? Or sometimes we call this as a plane wave extension. Huh? Okay? Okay, so now what is the form of, okay, so if I take r tends to infinity, because that is the region we are interested in the asymptotic domain, okay, so which is the term which depends on r? It is j, clear? So that means I need to figure out how j looks like when I take r tends to infinity, okay? So the form of j is like this, j l k r, so it goes like this, sine r. It's something sine kr minus L pi by 2 divided by k. So this is the asymptotic form of what? This Bessel function. Huh? So when r tends to infinity, this is the form. Clear? Got it? So now let's move to our problem. So remember this very formula. Okay, so what is our main motivation? We have to calculate what is the scattering amplitude, is it? So the scattering amplitude will give everything, okay? So this is our formula. So e raised for I k z plus f of theta phi. I will use now theta phi instead of k k prime because k k prime, f of k k prime means, so it is the angle between the what? K and k prime. Those are in spherical polar coordinates what? Theta and phi. Okay, so it's e raised for I k r by r. So what I know, this I know now. In spherical polar coordinates, I can substitute. This formula here, and I need to figure out this f of theta. Clear? But in this very equation, still one thing is unknown. Okay, forget about this very term. Let's assume I have known this thing. I can take everything on this side and calculate this f of theta. Clear? Got it? What is unknown to us? Unknown to us, this is psi again. Although this is actually the asymptotic form of the psi, but I don't know the psi. What is the form of the psi? Because the psi I have to obtain from the Schrödinger equation. Okay? And this psi should come from the Schrödinger equation solved in terms of the potential. Okay? In presence of the potential. So that means if I have to calculate this psi, okay, for this psi, okay, since it depends upon what? Both incident as well as, okay, so it has two parts, incident and the scattered parts, clear? So that means psi is a solution which you need to figure out in presence of the potential. Okay, so in other words, you need to solve this very equation. So what is that? Twice m by extra square e minus vr. So this is k square minus, so it's something like this, a square minus twice m v of r by extra square. Okay, sine, that's good. Okay, so now I need a solution. Since that psi, what we have written, that's actually the solution in the asymptotic regime, is it? Got it? So this psi is actually in the asymptotic domain. So So that means I need to figure out the psi from this very equation in the asymptotic region. Clear? Okay, so when I take the asymptotic limit, what will happen? So v tends to 0. Okay? So when I take, okay, in the asymptotic limit, this tends to 0. Clear? So it means it looks like the same equation what we have solved. Got it? So that means the solution psi should look like the same way. So it should have the same form. But where is the difference? So since it is actually the scattered wave, okay, or it is a wave which you obtain after the scattering in the asymptotic domain, there should arise actually a phase shift. Okay, let's think, okay, so let's put it this way. Okay, so first point is, have you got the form of the psi in the asymptotic domain will be of the same form, except these coefficients, that AL, got it, except those coefficients, okay, there can be some another coefficients as well, I don't know, but the form, rest of the form will be same. Clear? So you can change the coefficients. Okay, one more point is that when you look in the asymptotic domain, what will happen? So there should actually occur a phase change, because ultimately when a particle gets scattered by the potential, the light, the scattered, the particles what you receive, or the waves you receive, they should have a phase change because of this very potential. Got it? Okay. So how we can understand that? Let's put an intuitive idea how this occurs. Let's say you are having an attractive potential. What will happen to the particle? Particle will get, okay, think classically first. When you are having an attractive potential, particle will get accelerated. It will get attracted towards the potential. That means it will have a certain kind of acceleration. Okay. So what will happen to the wavelength? So wavelength will change. It will get shorter. Okay, in comparison to the original thing. So in other words, if I am having a repulsive potential, so the particle can get repelled by the potential and it will suffer a wavelength change again. So the wavelength will become longer. Clear? So ultimately, what does it mean? It means, so whether you are having an attractive potential or a repulsive potential, the particle which hits the potential or the target, so it suffers a change in phase in terms of waves if we look. So it will always suffer a change in phase. Because of change in phase, it gives rise to this kind of notion, whether the wavelength will become shorter or the wavelength will become longer. Clear? Ultimately, when you are having let's say you pass a light beam through a medium, what suffers? What you get? You get actually the change in phase. Got it? That gives rise to the change in wavelength. Got it? Okay, so that means what I will do, okay, so let's write then the wave function. This psi I can write as, in such situation like this thing, let's write summation of L equal to 0 to infinity, some AL. So AL is a constant which we need to figure out. Clear? Okay. So then I will write the same thing. I raise for L. Okay, so let me write carefully. Okay, so I should, okay. So it is 2L plus 1. Then you are having, what is J in the asymptotic limit? Sine, okay, KR minus L pi by 2. Now I will introduce a phase that will depend upon the angular momentum. Clear? Obviously, in which angular state the particle is being scattered. Clear? Okay. Then you are having PL. So, the spherical nature of the wave is actually given by these spherical Bessel functions. Okay? That's why I have introduced a phase here, and I have introduced the constant L. It will depend upon the L. For every angular momentum state, it will be different. Clear? Okay. So how many formulas you are having at hand? Now you have figured out psi in the asymptotic limit. Clear? So I know now the psi in the asymptotic limit, but the form of psi in the asymptotic limit is this thing. From there I can obtain what? This f of theta. Okay. So therefore, okay. So let's write this psi. So I will write therefore this f of theta phi e raised for I k r by r. So how much time is remaining?
10:31.
Okay, so let's stop here. Huh?